interrupt it as I go along. Otherwise, I'll just run through the whole thing, and it'll be 7:30, and I'll be done. And but I'm happy to engage with questions as we move forward. So I'd like to start with how we figured out where the future is. So as president, my responsibility, of course, was making sure that we don't have catastrophes this week or next year. But the real job of president is figuring out where the Institute needs to be in 25 or 50 years so that we can continue to do what we've done for 150 years, for another 50 years. A daunting task. And I have yet to find a crystal ball that doesn't get pretty fuzzy out beyond 5 years. And so I thought, how do I figure out how to help guide the Institute toward a future that I can't see? And I realized that one way to do it is to think about the future we're living in today and figure out where this future came from, and then maybe I could extrapolate from there to where the future is going to be in the next 25 or 50 years. And as I thought about where we are today, being able to project from my computer onto the screen, my guess is probably all of you. I usually hold up my cell phone and say, how many of you have one of these? But that joke's gotten kind of old for me. But so we live in this digital world, and if we think about what technologies have transformed the 20th century, what really changed our lives, there are a lot of fantastic technologies that we have today that we didn't have in 1900. But if you really think about the things that have been most transformative, they are digital technologies. And how did that happen? And as I thought about how that happened and talked to people and listened to people, it became very clear that digital technologies emerged from another convergence. So the convergence that precipitated the 20th century technologies was a convergence between physics and engineering. And how did that happen? So I'm going to talk a little bit about that, and then kind of lead you through my thinking of how I think about where the future is going to come from. And I think we are in the midst of another technology revolution that's going to come out of, and is coming out of, the convergence of biology with engineering. So I'm going to lead you through that story. I'm going to get to some policy implications, if not policy commandments. I did not pay very much attention to policy. Let me make that sentence clearer. I did not pay any attention to policy until I became president of MIT. But the president of MIT has played a very significant role in helping to guide the nation towards sound policies for education and research since before World War II, but starting in World War II, MIT really stepped up to play a really significant role in navigating policies to the future. And as I became president, I picked up that responsibility also and became very involved in helping to set policy going forward. It was mentioned that I co-chaired the Advanced Manufacturing Partnership for President Obama, just one example of my engagement in Washington. So I'll give a little bit of sense of policy directions, but happy to again engage in conversation about it. So the future we're looking at, we can be Malthusian about it. I'm sure many of you have heard of Robert Malthus. 1798, wrote this extraordinary demographic analysis, saying basically, oh my God, that if you go back and look over time, population growth rate is faster than the rate of agricultural productivity growth. And he looked back and he said this has happened through cycles, through time, and every time we get to a crisis point, the same thing happens. War, famine, pestilence, a lot of people die, you reset the balance, and then you start again. And so he looked at the history of mankind as just this continual kind of battle, trying to figure out how you're going to reconcile population growth with agricultural productivity growth. And he said it always ends the same way. That was in 1798. He was wrong. He was wrong because of technology. So farmers had started to use four-field crop rotation. So in general, people were letting a part of the field lay fallow for a year, and you didn't plant that, so you only had, 2/3 of your crop was actually producing useful food, and the rest was kind of sitting around for the year, taking a rest, so that it could, come back and be useful. But four-field crop rotation, where the fallow part of your field was planted with legumes, because the thing that your field was losing with every year of growing food was nitrogen, and the nitrogen had to be replaced. And so four-field crop rotation, a fabulous new technology, and fertilizer. So there was a big trade in guano because these great explorers that we've read about that sailed across the oceans to land in North or South America or in the Caribbean, what they found on their way were islands where seabirds were just pooping like crazy, and there were, hundreds of feet of bird dew, and that was a tremendous source of nitrogen. So there became a fantastic trade in guano for agricultural productivity. And so both fertilizer and four-field crop rotation actually changed the rate of agricultural productivity in Britain. It boomed, and the consequence of that was the population boomed, and if you want to have a positive view of this, just in time to provide the people that were needed for the Industrial Revolution. So my cartoon title of this talk is Cheating Malthus Again, because as we look forward to the projected population in 2050 of 9.5 billion people, we're roughly 7 billion today, the demands are astronomical. We have to double food productivity, we have to double our energy sources. I mean, there's just a lot of things we're going to have to do, and we don't have the technologies today to do it. And so there are Malthusians out there who are predicting the same kind of disaster that Malthus did. In any case, I'm an optimist. I think that technologies coming out of this 21st century technology revolution will provide the kinds of increases that we need. But let me tell you the story. So let's talk about first the convergence of physics with engineering. And I start with being able to change the slides, and that's not working. Let's see, there's got to be another way to do that. It's not that way. Let's try this. It's not that way either. And it's not that way either. Okay. So this doesn't, oh wait, that worked. Okay. Just required me to hit tab 3 times, not just once. So these are photographs of some of my great heroes. So these were the early physicists. They probably didn't call themselves physicists. Michael Faraday studied the behavior of electricity and electromagnetism. He had no idea what gave rise to it, but he described the behavior in exquisite terms. Didn't know what the components were, but in 1897, J.J. Thomson discovered the electron. And this really began to open the kind of the workings of the physical universe. So the discovery of X-rays, any number of things, gave us essentially a parts list of the physical world. Now I have to remind you, because now we know what the product of that parts list was, like the electronics industry. But like every age, like our own, there were people who said, why the heck are you messing around just playing with this electromagnetism stuff, because what good is it for? And it may be apocryphal, but there was a, oops, sorry, there we go. Sorry, I wasn't on the right side. So this is Faraday, this is Thomson. It is said that William Gladstone, who was basically the Secretary of the Treasury, said to Faraday, what's the use of this? Why would you bother? And Faraday said, the use? I don't know, but someday you will be able to tax it. And indeed, I paid some tax when I bought this computer or my iPhone. So this is going to be an ongoing theme, is that what we've understood is you have to be able to supply the components for future technologies before you know what those technologies are going to be. So no company can afford to do this. And it becomes the responsibility of federal governments in forward-looking societies to actually create conditions so that those basic scientific discoveries can be made, which later on will become something important. One of my favorite examples is an MIT example, of course. Carl Taylor Compton was perhaps MIT's greatest president. He was president from 1930 to 1949. He was a physicist. You all probably can't even imagine what MIT was like in 1930. There was a little bit of physics, not very much. There was a lot of really good engineering, the best engineering probably in the world already in 1930, but not so much science. The corporation, looking for its new president, decided that MIT really needed to step up its game in fundamental science. And they went to Princeton and asked Carl Taylor Compton to be president. Compton said, why me? I would never do that kind of thing. I would never expect to do that kind of thing. MIT doesn't do much in physics. I'm a physicist. And the corporation said, no, we want MIT to step up the game in physics, and we want you to do it. So Compton came to MIT, and in 1937, he ended up playing an incredibly important role as one of the architects of the technology in World War II. But in the first, I would say, 8 years as president, I've read all the speeches, not so much. He's kind of messing around, figuring out how to make MIT better in physics and things like that. So in 1937, it was the 40th anniversary of the discovery of the electron. He said, this is a birthday we should be celebrating. And he wrote this fantastic, beautiful piece that was published in Nature. It ended up, last year I was president of the American Association for the Advancement of Science. He wrote this piece up as his presidential address when he was president of AAAS. Marvelous to follow in someone's footsteps like this. And he describes just how important these discoveries are, not just because they're beautiful, but because of their practical value. And his practical value, he goes on and describes all of the fantastic things that had come out already of having this physics parts list picked up by engineers into not just great discoveries, but also great technologies and new industries. Really a remarkable thing. Now, I'm going to put in just a little, one more comment about Compton. He was so far ahead of his time. He said, we get it, there's chemistry and there's chemical engineering. There was a Department of Biology, again, not so distinguished, and he said, we need a Department of Biological Engineering. And in 1942, believe it or not, in the late 30s, he wrote a curriculum for biological engineering. Vannevar Bush was then the Dean of Engineering, and he was the one who came up with the name biological engineering, so he was a big fan of this. So in 42, Compton had the Department of Biology renamed the Department of Biology and Biological Engineering. He got it, a few people got it. Clearly the biology department didn't get it, because in 1944 they said, enough of this biological engineering stuff. We are the Department of Biology, and they eventually, very shortly, became the Department of Quantitative Biology. So they got the numbers part of it, but did not get the engineering part of it. And he gave a lecture in 1936 called What Physics Can Do for Biology and Medicine. So he saw this future, even though the faculty, not quite yet. Now, another critical person in this whole story, of course, is Vannevar Bush, for whom this lecture series is named. I hope many of you have had or will have a chance to read this amazing piece, Science, the Endless Frontier. So he was the chief architect of the technology development during World War II. So he put together all the teams that produced the atomic bomb, sonar, obviously here at MIT, radar, great airplane advances, incredible technology pushed during World War II. And as the war was closing, FDR turned to him and said, look, we figured out how to make incredible technologies for war. Can we learn something from that and figure out how to develop technologies for peace? And in response to that, Bush wrote The Endless Frontier, Science, the Endless Frontier. And in it, he produced basically a blueprint for the second half of the 20th century in America. Obviously, there were things like the GI Bill. Little did I know until I read it that he didn't say just that we should allow the GIs to come home from the war and come to places like MIT. The playing fields were all just tents and little cabins for the returning GIs so they could come to MIT. You also said community colleges needed to be bolstered because we were going to need people with kind of industrial training to participate in the factories that were going to come out of this new technology push. He recommended a very, very dramatic increase in federal funding for R&D. He said we should continue the same kind of investments that we made during the war, during this time of peace. He said, importantly, we're going to invest in research, but we're going to invest in research. The money should go to universities, not to freestanding research institutes. So different, because in the middle of the 20th century, Germany, that had basically started the idea of doing research and education together in the 19th century, had left it entirely. Freestanding research institutes, educational institutes, and there the twain shall meet. And instead, in the United States, we have this very different model, which I think is incredibly productive for both education and research. So Bush laid out the plan, and FDR died. His successors were not as enthusiastic about this as FDR had been, so things were moving, but pretty slowly, until the shock of Sputnik happened in 1957, and all of a sudden, our leaders got serious again about investing. This is a quotation from one of the very many speeches that President Kennedy gave about the race to the moon. Now, you can say it wasn't a war, but it was kind of a war. Happily, it was only a Cold War. But we were terrified, terrified in terms of defense, terrified in terms of the position of our country in relation to the rest of the world, particularly the threat from Russia. But for those of you who can't read this is just so moving because he says we choose to go to the moon in this decade and do the other things, not because they're easy, because they're hard and because they're so hard. That goal is going to organize and measure the best of our energies and skills. So what Kennedy recognized, and you see it in many of his speeches, if we set out a national ambition, we will work together toward that goal. And it will make us do more than we ever imagined we would do. It will create organizations that we never imagined we would have. And each of us as individuals will be able to accomplish more than we could ever have done without reaching for that distant goal. And this has become, for me, just an incredibly important inspiration in terms of how we organize ourselves. Why do you have a university? Why do you have a university initiative? And it's because it does organize our best energies and skills. So people often ask me how I got to be a scientist, and I tell them I grew up under the shadow of Sputnik. And for me, it wasn't a shadow. It was a bright, kind of a spotlight saying, you can do this. You can go here. So this is a picture of me with my three sisters. We were little kids. And it just, I just was so compelled around this mission. And I have a little, now this is, kind of a little bit of revelation that I share with some, shall we say, embarrassment. However, I heard the call to action, and this is an essay that I wrote when I was in second grade, describing and illustrating that you could be a scientist, and if you were a scientist, you could figure things out. And for you probably can't read, happily you can't read the spelling. Maybe you could figure out how to go to the moon. Importantly, as a 8-year-old or 7-year-old, 8-year-old, I guess I said, but you can do all this hard work, but it would be fun. And that kind of has been, for me, one of the themes of my life. You do all this hard work, but when you're doing it with other people, it's pretty darn fun. Clearly, bad spelling, bad grammar, bad drawing. Had to be a scientist. There wasn't much else I could do. But the marvelous thing, it wasn't just me. It was a whole generation of people who were motivated around this ambition, that we believed that we could do more than we could have done on our own in service to the greater good. Very, very important. In any case, the convergence of physics with engineering produced an array of technologies. I discussed them before, really transformed our world. So that's the future we're living in today. Where is the future coming from that we're entering? So important. A physics parts list allowed engineers to pick up those parts and invent devices. Biology didn't have a parts list until the 1950s. And there were two important revolutions in biology. One was molecular biology. So before we knew that biology used DNA, RNA, proteins to construct living things, we didn't have any way to do things with biology. We could observe them, we could push things around a little bit, but we didn't have a parts list that allowed us to actually manipulate things the way we do today. So obviously the description of the structure of DNA, the central dogma, all of that, those marvelous insights from molecular biology that continue even today, was part of this transformation of biology into a more component-driven science. And we have invested massively in this. The second big innovation or revolution in biology was genomics. So it's one thing to go gene by gene, and something very different to be able to go many genes by many genes. The technology around this, as I said, is absolutely staggering. On the top line here is Moore's law, showing you the improvement in chip density, and the squiggly line is the descent in the cost for a genome. So the Human Genome Project was launched in about 2001, and at the time, to sequence the human genome cost $100 million and took 10 years. Some of you may know what it costs today. Less than $1,000, less than half a day, and getting faster and cheaper all the time. This has allowed us to do all kinds of things in understanding genes. Obviously, we are in frantic search and sometimes quite successful search of disease genes. Some disease, thank you. There's color there.
It's quite warm.
It's quite warm. Okay, I'll leave that. And there are monogenic diseases, and if you can get the disease gene, the idea is you can target a therapy to that gene. But there are more complex things. There's a fabulous study several years ago by Participati looking at cholera. So when cholera comes through your town, a lot of people die, but some people don't. And being able to understand the difference between the genetics of the people who die of cholera and those who don't die of cholera tells you something about how we can resist disease and gives you a strategy for building resistance among those who don't have it. This is an unspeakably powerful technology. So we now have a parts list for biology. When I arrived at MIT in 2004, the Dean of Engineering, Tom Magnanti, told me something absolutely astonishing. He told me that a third of the 390 faculty in the School of Engineering, I came from Yale, we had 45 faculty in the School of Engineering, so the 390 faculty, it's a lot of engineers. But a third of them, he said, are already using biology parts in their work. Interesting. We had a department of biomedical engineering at Yale, but it was biomedical engineering. And what Tom Magnanti described to me was various people in the School of Engineering using biological parts to do things that had nothing to do with biomedicine, had nothing to do with the genome, had to do with things that were really quite different. So it was when I started to see the future quite differently. So I'm going to tell you 3 stories about what I mean when I'm talking about the convergence of biology with engineering. They all follow the same theme. And this is a book I'm just finishing because I think it's important for, not you guys, you're too sophisticated and you know too much for the book to be for you, but it's for people out there who may pick up, the Science Times and read about one of these examples, say, nanoparticles that diagnose cancer, and they go, whoa, that's really amazing. And then the next day about viruses that make batteries, and they go, oh, that's amazing, but they don't understand it's the same thing. It's all the same thing, and this is, I believe, the technology story of the 21st century. 3 stories, they're not all from MIT. I've tried very hard in my book not to make all of the chapters about MIT, but I could have. And I'm going to tell them to you just briefly. So the first is a story coming out of the Koch Institute. This is Sangeeta Bhatia, who has an MD. She has a PhD, a MEMP PhD. She is a bioengineer and a biologist and a physician. So if we're going to have 9.5 billion people on the planet, and even today, medicine is too expensive. It's not accessible by many people. And frankly, in terms of disease, diagnosis comes too late. So Sangeeta has developed a way to do early, cheap diagnosis. Now, we're going to talk about cancer, but her technology can be used for many, many different diseases. What's the best approach to cancer? Prevention, right? Sometimes I wear sunscreen, sometimes I don't. And we know that there are estimates that over 30% of cancers are preventable. So prevention would be great, but prevention's not everything. So the second best approach is early diagnosis. So cancer is a disease that starts as a cell or 2 or 4 or 8, and eventually it's a lot of cells. It starts as a cluster of cells that probably no more than a millimeter in size. And eventually the cluster gets big enough for these cancer cells to be able to escape from that cluster and go someplace else. And it is metastasis that is the thing about cancer that kills you. So if you can diagnose cancer and other diseases early, you have a better chance of stopping it than if it's, all of the cows have left the barn. And so, but our technologies today, although they're better than they were, are still not good enough to catch cancer early. So Sangeeta has designed a technology which is, actually this is it's not her current version, but here's the way it goes. That she has a nanoparticle, this is a nanoworm, but she's now down to 1 particle. And she's decorated with little peptides. The peptides each have a site for a particular enzyme. Enzymes are proteins that can cut other proteins at very specific places. One characteristic of diseases is that many of them produce disease-specific enzymes. So you think I might have cancer? You give me this nanoparticle, and this little catalytic site for the enzyme is vulnerable to a cancer-specific enzyme. So if I don't have cancer, this nanoparticle swims around my vascular system, nothing happens to it, but if I do have cancer, it encounters this cancer enzyme. And the cancer enzyme clips off a little bit of that peptide. The nanoparticle is big, continues to circulate, eventually it gets degraded. They usually end up in the liver and get degraded. But this little peptide has been designed by Sangeeta's team to be small enough to filter through the kidney into the urine, where you can detect it. And you can detect it if you think about urine-based detection systems. They're over-the-counter pregnancy tests. I don't know what they cost today. $5, $15, they're cheap. Highly accurate. And that's the idea behind these nanoparticles that Sangeeta has designed. That you can multiplex them. There are any number of ways you could play this game, but the main point is you can get early detection because you're using an enzyme which amplifies. An enzyme can cut hundreds of different substrates. These peptides, these nanoparticles can generate a signal in the urine, which is found by very, very sensitive assays, and we know how to do that. And so the potential exists that you could have an annual exam that can tell you whether you're incubating some disease. Very powerful. She started a company called Glimpse Bio to get it off the ground. But in their studies, they believe that they can detect a cancer mass that is 10 times smaller than can be detected right now by standard imaging, standard blood tests, any of our normal assays. So 10 times, that's several months, perhaps even several years in advance. So that's actually a great way to think about making medicine more accessible and less expensive. The second story is Angie Belcher. I don't know how many of you know Angie Belcher. She is a biological engineer, materials scientist, an amazing MacArthur genius, and she's fascinated by, she went to graduate school at UC Santa Barbara and loved walking on the beach and fell in love with abalone. So here she's holding an abalone shell, a big abalone shell. And she says, this is an amazingly strong, I don't know how many of you have seen these shells, they are incredibly strong. And she said, but it's just calcium carbonate, it's chalk. I mean, it is, I had one right here. I mean, this is nothing, right? It's not very strong. But what the abalone does is it makes a little bit of protein that knits together calcium carbonate crystals into a shell that has the strength of stone. And then when the abalone dies, the thing just disintegrates, goes back in the ocean. So the next abalone can use those same components to build a shell. And she says if nature can make these fantastic materials, why can't we? And she realizes that we could do it, but it's actually a little easier to get nature to do it. And she has used M13 viruses, which are standard benign lab strains of virus, to organize battery components. And she has figured out how to get batteries. This is an M13 that's been decorated with some battery components here, to organize themselves into batteries. These batteries that she's built in the lab have the same charge density, the same capacity for recharging as state-of-the-art lithium-ion batteries. That's all pretty cool. But what's coolest, in my mind, is that the viruses make batteries at room temperature and without any toxic byproducts. So, I don't mean any disrespect, but, we all love the alternative energy technologies, and we think they're really going to win the day. And the big ones are solar and wind. They're the highest capacity alternative energy technologies, but our storage ability is insufficient to make either wind or solar something really viable. The sun doesn't shine, the wind doesn't blow, and you're in trouble. More seriously, in my mind, than not having great battery technology, not having enough, the solution is not solved by building a new battery plant that is the size of Texas. And you know who I'm talking about. Because battery manufacturing is incredibly energy intensive. The temperature required to make batteries is enormous, and it spews out toxic byproducts. So you can make a big battery plant, but that's not going to give you sustainable energy. You'll be able to store it, but you will have polluted your environment. So Angie's batteries, the viruses make these batteries, room temperature, no toxic byproducts, and they are just as good as commercial batteries. A very promising technology out of the Convergence. The third example is not from MIT. One of the things we desperately are going to need, we already need, is pure water. Of all the water on Earth, 70% of the Earth's surface is water, but you know, I think it's less than 0.1% is water we can use. Very little of it, 3% of it's fresh, and of the fresh water, most of it's in, you know, ice caps and in groundwater. You can't really get at it. So very, very little water is available to us, and we know that there are water-starved nations. We know even in the United States there are water-starved parts of the world. So we have to purify water, and here again, the technologies for purifying water are also energy intensive and frankly pretty inefficient. So this is a fantastic science story. All of our cells, all of the plant cells, all of the cells everywhere regulate water. They have to, because they're, you know, they're nicely puffed up. And that's a feature of having enough water inside them to, you know, keep the membrane in a, you know, in a like shaped like a balloon that's blown up rather than a balloon that's collapsed. And for decades and decades, people sought what they assumed would be a water channel, and no one could find it. And they finally just said, we give up. There isn't a water channel. Water diffuses across membranes, and you know, does osmosis, but just by plain diffusion across membranes. And everyone kind of accepted that. Peter Agre, who's a hematologist by training, a fantastic guy, decided as his science, for his science outside of his clinical practice, was he would find the Rh protein. Now, most people, we don't care that much about the Rh protein. The Rh protein is a blood group protein. It's on red blood cells. Before it was understood at all, it was a cause of death of babies, because if my Rh factor does not match my baby's Rh factor, my immune system will attack the baby's Rh protein on blood cells and damage or destroy the baby. So that was figured out vaguely, and an antidote was figured out, which is just an antibody that counteracts the ability of the maternal antibody to recognize the baby's antibody. And that was fine, but no one really knew what the Rh protein was. And so Peter Agre said, I'm going to find the Rh protein. I'm a hematologist. I'm going to figure all this out, figure out what it normally does, and this is going to be great. He took a boatload of red blood cells. He purified the membranes. He purified the protein. He got a band on a gel. He put that band in a rabbit. He made antibodies, and it was the wrong protein. It was not the Rh protein. And I don't know, how many of you are scientists? Yeah, you know what this is like. I mean, this is like maddening. So, having done the experiment myself, not on the Rh protein, but another protein that I missed. So what do you do? So, I mean, what you do if you're a sensible person is you say, okay, that purification didn't work. I'm going to go back and get the Rh protein. But Peter Agre is a bit of a nut, and he just couldn't get this protein out of his mind, but he couldn't figure out what it was. And he tried, and finally, a former mentor of his, when he was complaining about this protein, said, I bet that's the water channel. And Peter Agre said, there isn't a water channel. What do you mean? Decades of people have shown there's no water channel. And this friend of his, Parker, says, it could be. And so he went back, and indeed, he had discovered the elusive water channel. He got the Nobel Prize for it, so it's okay. He didn't go back and study the Rh protein. But so he discovered aquaporin, and that's illustrated here. What an amazing molecule. So it sits in membranes. Most aquaporins are entirely selective for water. The structure of this thing is fascinating. The biophysics are amazing. Absolutely, he did all kinds of studies and published them. And there was a biophysicist named Peter Jensen, who was a biophysicist entrepreneur, and he saw this, the paper that demonstrated the structure of this, And rather than saying, hey, that's cool, I'm gonna go find the water channel in, Armadillo or something like that, he said, maybe we could use that protein to purify water. So he started a company, which is called Aquapor, and it's outside Copenhagen, and they are making filters, water filters, using the aquaporin protein. So that any of you who know about biopharma, you know that we know how to make proteins in large, but the proteins we make, like for drugs, for antibodies, are soluble proteins. So the challenges for this company to actually build membranes out of a membrane protein have been enormous, but they actually now have water filters in homes in China. And Jensen says, why don't we just use nature's genius rather than busting our brains trying to figure out how to filter water? It's a brilliant and I think very promising technology. So, 3 examples, all in the same theme. But they require people to cross disciplines. We require biologists and engineers to actually talk to one another, because no one is coming out of school, educated sufficiently broadly. And this is really difficult because our structure in our universities, MIT is a little better than most, is we have a department of chemistry, we've got a department of mechanical engineering, we have a department of mathematics. And how do you get people to talk together across these disciplinary silos? I'm a big believer in disciplines. I think you really do have to study down a very, very deep channel in order to know something important, and also to understand how knowledge builds on knowledge. However, to actually get something to work in the real world, you've got to be able to do crosstalk. So we face an innovator's dilemma. Our universities do pretty well. Our current academic structure does pretty well, but not well enough. When we put together the Koch Institute, and I'm going to talk about that in a second, we realized that engineers and biologists use different languages. They have different vocabularies. They define problems differently. How the heck do you get these people to be able to work together when their operating premises are just very different? Obviously, we have institutional structures that are inhibitory, and funding, oh my goodness. The NIH funds biology and biomedicine. The NSF funds engineering and computer science. Neither of them fund things that cross, and so it's very hard to get this stuff funded. The thing that has saved the day for us and others has been private philanthropy, because it's fast and they'll fund you to do crazy things. So one example of a way we've gotten it to work is in the Koch Institute for Integrative Cancer Research. This is one of the things we started when I was president. Importantly, there is, you'll hear this theme again, a shared ambition. Tyler Jacks, who's the amazing director, said to the faculty that were in the Center for Cancer Research, we're now going to study cancer. Before that, they had done fabulous biology. There were 12 faculty recruited to the Center for Cancer Research when it started in 1974 during the War on Cancer, and 4 of them have won the Nobel Prize so far. Pretty good biology, you've got to start somewhere. But Tyler said, we're now going to do cancer. One of the wonderful things about what's made this work is that all the faculty in the Koch Institute have departmental appointments. So they're either the biology department or the mechanical engineering department or material science. We don't care what department they're in. What we do care is that they're putting some of their work at least to cancer. We architected the building to increase the possibility of crosstalk. Every floor, except for one, has both scientists and engineers. And actually, this was the original plan, and now, with a couple of new people coming and going, it's even more mixed up than it looks in this plan. Importantly, one stairwell, one set of elevators, one cafe, one set of bathrooms. So wherever you go, you're going to run into someone who doesn't speak our language. When they launched, there were a lot of just educational sessions, so we spent a lot of time, and I think the theme of the building still is, you can't ask a stupid question. So there's just kind of an agreement that if you don't understand what I'm saying, because I'm speaking biology and you speak engineering, you can stop me, and I will explain it without insulting you. That usually works. The Koch Institute is more than just the building. We're in this great place, so we can have direct access to the Whitehead and the Broad and the departments of chemical engineering and biological engineering and ECS. So that's really great. It increases the mixing rate. But one of the things MIT doesn't have, happily, as president, I was happy, we don't have a medical school. But if you're studying cancer, you want to be able to see the disease. So a lot of academicians cure cancer without having ever seen it in a person, and often those approaches don't really work when you get to people. So it's very important, if we want to accelerate progress, that we have colleagues. established the Bridge Project, which links us to the Dana-Farber Harvard Cancer Center and the literally thousands of oncologists that are just across the river, and delighted to be able to collaborate with MIT. Now, the building is called the Koch Institute because David Koch was enormously generous in giving us the funding for the building and a lot of professorships. The Bridge Project, also private philanthropy. It is very, very hard to get funding for these kinds of things, and so we have relied on bringing other people along to be part of our team. I talked about the challenges of the 21st century. We need better and more accessible healthcare, we need sustainable energy, and we need more food and more water. And I do believe that these technologies will be part of the solution. Now, at MIT, we understand that federal investments in basic research is the raw material for innovation. And one of our great Nobel Prize winning economist, Bob Solow, actually did a study in the late 80s that showed that half of the economic growth in the United States since World War II was attributable to technology. It wasn't people, it wasn't product, it was just that new technologies had come along. A very, very important insight. And with Vannevar Bush's articulation of the purpose and Sputnik, we were investing enormously in this. And this is, I don't know that you can actually see this, but most important is the red line. This is federal investments in R&D. We had I present it as relative to GDP, and the reason I do that is how much can a nation afford? It's not a dollar amount. It's what fraction of our resources are we going to put into our future. The peak was in the mid-1960s, where we reached 2% of GDP. It has fallen now, we're down at around 0.8% of GDP. Now, overall, we still have a lot of funding. A lot of it has been picked up from business, and that's just great. I love when industry funds research, but they're usually funding the D side, the development side, not the R side, and so we end up, strangling the resources that will eventually be put into development. So this is, in my mind, a very, very serious problem. And one of the fabulous things about the middle of the 20th century is the United States was doing this essentially by ourselves. Other nations didn't have the resources or the vision to basically bet their future on these kinds of investments. However, that is not true today. So this shows you the United States in the red line over time this is just showing you from the 1990s up until a couple of years ago. Again, reflected as percent of GDP, and Japan's above us, South Korea's above us, Germany's now above us, and that is all fine. I would like the United States to continue to be the leader. It's unlikely with this kind of expenditure that we will, but I'll tell you, it's this line that is so staggering. This is China, and within another couple of years, China will be spending more of its GDP on R&D than we do. And I'll tell you something else that was just so incredible. Almost every week when I was president, someone from some country would be in my office saying, we get it. We know how the United States came to dominate the world economy in the second half of the 20th century. We understand what we need to do. Just tell us how we build a university, like MIT, that will allow us to do what the United States has done. And I would start the conversation. They said, no, we just want to do engineering, except for China. Our colleagues from China would come and say, we understand we want to do math, we want to do physics, we want to do chemistry, we're going to do the basic science too. And so I think the amount of money China's putting into this is staggering, fantastic. I think we have some real problems in terms of keeping up. In terms of federal policy, now this is the policy part for you. You've got to start with fundamental research. We do not have sufficient flexibility in our funding. I described the problem of funding this cross-disciplinary research. It doesn't. Every once in a while we get it together. We had a national nanotechnology initiative that brought money together from a number of different agencies. We now have the BRAIN initiative, the Human Genome Project. So occasionally we figure out how to do a one-off. We don't have any systemic way to fund these kinds of cross-disciplinary activities. France Cordova, who's head of NSF, has committed the NSF to Convergence. I hope that'll happen, but frankly, NSF is not the big funder in the room. It's the NIH. We have to invest in innovation, and one of the things that I think you probably will resonate with, because one of the things that MIT does very well is tough tech. So I did an analysis when I first arrived, saying what's the difference between MIT and Stanford, between the Boston region and Silicon Valley. It's just the proportion of software versus hardware. And so if you look at these studies that show the number of companies that you all spin out, it's it's about the same if you do it relative to the number of alumni, but the composition is different. And so Stanford just does a whole lot more software. We do a whole lot more hardware. Hardware is harder. And the return is longer. And so our federal policies currently do not sufficiently support long cycle, capital intensive industries. Every one of the projects I described, it takes a long time to get those products developed and out into the world. So our policies currently do not favor the kind of tough tech that really is the path to the future. So this is again one of my favorite quotations, and I'm always a little embarrassed when I put this up. Does any of you know who Edwin Land was? Has any of you ever heard of a Polaroid camera? So, of course, when I was growing up, this was like a miracle, that rather than having your film out of your camera and taking it to the drugstore and waiting a week for it to come back, the picture just developed. Edwin Land was a genius. He did a lot of neuroscience, and he actually understood that, as he says, that the periods of spectacular human advance are times when we figured out how to converge disciplines. And this has been, everyone has known this forever, but actually making it happen is hard. And I think making it happen now is really incredibly important. This is clear. So let me just, finish by saying that I think that the convergence of biology with engineering holds the seeds of the technology solutions for the 21st century. I would love it if we had a national ambition. Choose it. Is it healthcare? Is it energy? Is it water? Is it food? Can we not assemble a national ambition that would motivate people to actually put their shoulder to the wheel in the way we put our shoulders to the wheel that got us to the move in 1969? So with that, I'm running late, but let me end and let you ask any questions. I'm clearly an enthusiast about it. I've become a total monomaniac about this, but I really do think that this is going to be the 21st century technology story when you guys get out into the 22nd century. I'm not going to be there, but you'll enjoy the products of it. That's it. Thanks. Yes?
So if you could go back to the slide previous where you were talking about the different ambitions. I know for me, as someone sitting in the Boston biotech area, there is a big emphasis on healthcare. And there seems to be more VC interest in agricultural industry, but the challenges for water and energy in that space are still pretty large. So I was wondering if you could speak sort of to where you see that sort of push coming from outside of like the academic environment.
Right. So I think, we just launched a new company with help from Eni, the Italian power company, Fusion. That's not this, but it is an evidence that some of the big energy companies do invest. And we had, actually Eni invested in our solar project out of the Energy Initiative also. Battery technology was unchanged for about 200 years. And, again, one of the great surprises when I got to MIT was, eventually about 24 new battery technologies. And so I think people are interested in it. The real problem, I think, isn't that it's energy or water. The real problem is long cycle, capital intensive industry. So people now know that you can make a lot of money in healthcare, and so people are willing to invest. But I think there are some reasonable investments in new battery technologies, new energy technologies. That said, I have been biting my nails every time annually with the new budget. I have been relieved in the first couple of Trump era budgets that ARPA-E, which was the Department of Energy's kind of experiment for alternative energy technologies, despite all the pontificating out of the White House, Congress approved ARPA-E's budget and actually increased it. This year they've reduced it, so now I'm actually quite concerned about the impetus. And the idea that the federal government is agnostic to new technologies is just dumb. Of course the federal government is not agnostic about new technologies. You've got to place your bets. The NIH isn't agnostic. They don't fund anything. There are things where they think are promising and they fund those things. And they know what they want to fund based on what experts in the field think are the promising directions. And so, probably my greatest concern is about the future of energy. And also, this is no secret. What do you think China's doing in energy? What do you think Germany's doing in energy? It's not what I often joked about. I said, well, do we want to go from buying oil from undependable countries to buying new energy technologies from undependable countries? That's just lunacy. And so I am concerned about where the new energy technologies are going to come from, and I don't think we are well positioned in our nation to be the source of new energy technologies. Food coming along, okay? But those the food companies, the agribusiness understands very well the incredible need, and that there's a lot of money to be made in next generation food. So I have to say I'm less concerned that that's going to get figured out, and currently the dominant companies are U.S. companies, so there's a lot of industry investment. Yes?
Thank you. Thanks for the terrific sharing. I really enjoyed it, and I'm a future student of the Sloan Fellows, so I'm
Great.
from China's manufacturing industry. And these days I'm here to talk to different people to figure out some entrepreneurship ideas in optimize the operations in manufacturing. But to my surprise, not many people nowadays, even in the operations research center, have a focus on manufacturing. Most of them are digital commerce or anything or other things. So I think one reason is because now there are not enough data points in manufacturing compared to the digital economy. But there are a lot of problems need to be solved in this area, many of them. So I'm from a small manufacturing company, so they have a lot of difficulties in operations, in people management, etc. But it seems not enough resources or focus are put into the research or help those manufacturers. So how, but all the nations are stressing the importance of manufacturing. So how do you see the potential, or you are optimistic, right?
Yeah. Well, I'm optimistic to a degree. So I think that the future of manufacturing is incredibly exciting. I just came off the board of GE, and I'll tell you a story. So I'm sure that this is debated, but 3D printing may have been invented at MIT by Mike Sema and Emmanuel Sachs decades ago. Well, maybe not. Yeah, a few decades ago. And so when I first arrived at MIT, Manny Sachs brought me this cute, adorable 3D printed model of the main group. I have it in my office still. It's with plastic. And so when I first arrived, everyone had a plastic 3D printer. Whoa, very cool. Every place I went, someone showed me the trinket, that they had made out of 3D printing. I said, oh, plastic, great. I went to the GE Research Center. I just joined the board. It must have been 2005, 2006, I guess. And someone there said, here is a 3D printed metal part. It looked like, I don't know if you know this expression, the dog's breakfast. I couldn't imagine how you could ever use it for anything, because it was just, 3D printing in metal is very, very hard. But now GE is making jet engines that have fuel nozzles that have been 3D printed, and has really, kind of tripled down on 3D printing, because that is part of the future of manufacturing, and it's incredibly exciting. But, a big, innovation curve between where 3D printing was 10 years ago, 3D metal printing, and now. I don't think, and part of President Obama's effort was to recreate manufacturing, thinking about what the future of manufacturing was, rather than wringing our hands thinking that we should go back to old manufacturing, figuring out what next generation manufacturing is. I think it's really exciting. GE also, as you know, is very interested in digital tools to make manufacturing more efficient and more effective. And so I think it's very promising. I admire what China's doing in terms of, really getting their hands around next generation manufacturing rather than last generation manufacturing. In the United States, I don't know that we're going to do it. We started up a bunch of manufacturing innovation centers. If you were interested, you could go visit them. I think there are probably a half a dozen of them now around the country. And these manufacturing innovation centers are collaborations between universities and industry, a couple of industries focused on different technology. Each of the innovation centers focuses on a different piece of manufacturing technology. And my guess is that's where you're going to find the future of manufacturing. And I very much hope that we will be able to persuade investors to take this seriously as the path to the future. Software is great, but I think that at the end of the day, we want computers. We need stuff. Obviously, so it's a great question. And you're just starting Sloan Fellows now?
This June.
Great, wonderful, welcome. Yes.
So you said you didn't become involved really in policy until you had become the president of MIT. Had like a great career as a scientist, so that I guess you could become an influencer or have the capacity to influence policy.
Mm-hmm.
But for like early career scientists who do have that interest in policy and creating funding for like those cross-agency collaborations that you talked about, but are also interested in remaining scientists and following our scientific careers, do you have advice for us in what like roles there are as early career scientists to kind of, I don't know, like initiate or be involved in those cross-agency collaborations or projects like that, or just kind of like get involved in influencing, driving that cross collaboration?
Absolutely. So obviously, from my perspective as AAAS, there's a Science Fellows program there.
Right.
And MIT has a summer internship, has a lot of things where you can learn about how policy is done. I have to say, I didn't have a clue how policy was made before I became president, but I had Bill Bonvillian taking me to Washington every month and introducing me to the right people and making sure that understanding where there was a moment of change and where my voice could make a difference in making it go in the right direction or the wrong direction.
Yeah.
I hope things go in the right direction. And so we have a number of resources through at the MIT Washington office. But beyond that, there are policy fellowships. The hard thing, so those are two, I would say, very different directions. And I know a lot of people now in Washington who are scientists by education, but are policy wonks now, who are in the mix. One of the things that we lack, and I'm evidence of it, is that I grew up in science without any appreciation of the importance of my voice in carrying the message out. And I think that being an educated and informed scientist and policy aware, will be increasingly important.
Right.
One of the things scientists have done very badly, and I would say it's something that I've worked on through my whole career because I am interested. I've always been interested in communicating to non-scientists what we do. We're just not very good at that. One of the things I'm pushing very hard at AAAS right now is, we publish science. And truth be told, when you ask anyone how much of science they actually read, everyone reads the front page parts and very few people can read anything in the back part. But the front part, my view is, could be easily adapted for general audience. There is not a good general source of science information, and I'm hoping the AAAS is going to move in that direction to produce something just so we can tell the world. But I think all scientists need to spend a considerable amount of time communicating to the rest of the world. Happily, as president of MIT, I had a lot of opportunities to talk to all kinds of audiences about the importance of science and technology and the importance of investing in basic research. I was at a pharma meeting days, and I guess it was earlier this week. They said, well, shouldn't universities be doing more translational work? And I thought, maybe it's just not what we're really good at, and it costs too much money. We're much better at creating the solutions for problems that we don't know exist yet. And the hard part is, industry has a set of very well-defined problems that they guard jealously, because if I knew what the problem was, I might be able to find a solution. And the university is a basket of solutions, and how you figure out how to match the problems to the solutions is a bit of alchemy. MIT has figured out how to do that amazingly well. It often just has to do with people having conversations with one another. But I would definitely, suggest, keep at doing both. We need people to do it.
Can I ask a quick
Yep.
follow-up question?
Yep.
So a more specific question maybe be like, how far in your scientific career do you have to go, and how well established do you have to be to really have that influence? Because I know about the AAAS Fellows programs, but I'm wondering, like, people like you and I guess like Tyler Jacks is on Obama's like advisory council. Like, how far do you have to go in your science career to really have an influence on, I guess, like high-level policy changes? And I guess I don't really know how much AAAS Fellows have an influence on policy changes, but it seems like in my mind, very well-established scientists are the ones who are in these positions of change.
So very well-established scientists are the names that you read.
Right. Okay. That
But
makes
the
sense.
work gets done. It's like everywhere. The work gets done by people who understand well enough, what the issues are to be able to implement the things that need to be done day by day.
Right.
So you can be sure that Tyler Jacks was not doing the fundamental stuff to put the cancer moonshot together, right? So other people were doing, but Tyler Jacks is the name brand that gets
Yeah.
people's attention and assures people that this is going to be good science. But truth be told, there are other people who aren't Tyler Jacks yet, who are doing all of the knitting together. We've done a couple of reports on Convergence, and there's a small army of scientists, right, and engineers who are early on in their careers who have spent their time helping us to put the reports together, gathering information. It's like, like in a lab.
Okay.
Yeah.
I'm a visiting PhD student at MIT Energy Initiative from Germany,
great.
so I was interested to hear what you had to say about that. I was interested especially in the alchemy that you described before, and how to, so you had said there's a base research, there's translational things, and then you have to bring together the people who understand the problems with the people who have the solutions. So I'm really interested in how to do this in this bioengineering and also, for example, chemical engineering part, where you already said there's a high demand for funding, it takes longer, maybe the risks are higher. So what do you think has to change in this alchemy for bioengineering?
Yeah, so so the Energy Initiative was another one of the very big initiatives that we stood up when I was president. And there again, the reason we could do the things that we did was we had industry funding. And having industry as our partner was critically important because they understood the problems. And the academics can kind of imagine, how hard it is to check out the integrity of an oil pipeline. Yes, the people in the field know how hard it is to check out the integrity of an oil pipeline and what kind of sensors you need to actually, can help you design them. They don't know sensor technology, but they do know what the physical limitations are and the physical demands. And so creating conversations between industry and academy, I think, is absolutely critical. And of course, it helps to have industry resources moving that ahead. The very fundamental research, it's impossible because, it's like Faraday. I mean, he didn't know we were going to have TVs, right? So, so the very fundamental research has to be, frankly, can't be funded by industry. It has to be funded by federal governments. What MIT has done, not just to the Energy Initiative, a number of the companies that are partners in the Energy Initiative have scouts here at MIT. I don't know if you've run into the people from one of the companies that's just kind of around talking to people, figuring out, where the match is. And so I don't know that there's any more efficient way to do that alchemy, besides being sure that there are people with shared ambition who are actually sharing the conversation.
What about new companies, starting new companies?
This is going to sound braggy, but the MIT, there was a study done recently out of Sloan that showed that MIT doesn't really have any problem starting new companies, that not every person, every faculty member or student wants to do a startup gets to do it, but we're very good at startup. The hard part for these tough tech stuff is scale up. Very expensive and hard. So we started the Engine, which is a tough tech incubator, basically a place where the kinds of machinery and the knowledge that you need to build physical things is available for people who are starting companies. So it's scale up. A lot of universities complain about startup because of where we are, particularly in biological engineering, startup is not such a problem. I ran into Bob Langer the other day walking to parking lot. Bob Langer is the most prolific biological engineer, I think, in the world today, and I've forgotten what he said, that he now has, you know, who knows how many, over 1,000 patents, and he started 40 companies, and the companies, he says, it's not me, it's my students. And so the way you do it is by finding people who have done it before and having them help you walk the path. Yes?
Just following your comment on communicating to the general audience.
Mm-hmm.
So technology is more and more closer to the public. So it entered our house, now even our bodies. So how can we reach, as scientists and engineers, how can we reach correctly the general audience and to bring him into the conversations regarding new technologies and boundaries and ethics that will involve the new technology of the future?
So it's a hard thing to ask of you, but all of us live in communities, and you know, everyone wants to know about these things. And so through schools, through libraries, through community centers, you know, if you go to a church, you can offer to, you know, give a talk. If you belong to a music group, you can offer to, you know, you talk to people about it. So what really works is bootstrapping your way up, but finding, you know, asking, just volunteering, saying, you know, want to come over to my house and we'll talk about this, or let's go out and I'll tell you about this. So it becomes difficult if one is entirely monomaniacal and you don't talk to anyone except the people in your lab. Then it's harder. But I always encourage people to think about the people they know outside of their science. And is there not a way that you can share what you do with them? People are afraid to ask because we frequently insult people who don't understand our vocabulary. And so I think part of it is learning and practicing. I felt like I used to practice with my parents, who had no idea what I was working on. But I figured I had some success when I was able to explain to them what I was doing. Or schools. I mean, if you've got kids, you know, you're seizing an opportunity to, you know, go talk to a school class, or teachers. A lot of opportunities, but easy opportunities, not gigantic things. So not going to the venue where Tyler Jacks is speaking, but using the venues where they'll really appreciate hearing from you. People love understanding this stuff. It's my general. I was telling one of my neighbors once, you know, recently about the book, and a lawyer, a trust lawyer, and I was explaining the energy chapter, and she said, I can't imagine anything more boring than batteries. I thought, okay, there are some people I'm not going to reach. There are just some people I'm not going to reach. Other questions? Well, it's getting late. Thank you all for your attention. And it was a download of a lot of information. I apologize, but I'm really passionate about it, and I'm delighted that MIT is doing so much to make it possible for all of you to help invent the future. Thanks.
And just as a closing statement, if thinking more about how you can impact these funding decisions and talk to lay people about these ideas is something that you want to grow in, the Science Policy Initiative puts together a congressional visit day every year where we train you on how to talk about these issues with non-scientists and travel to DC to advocate for these issues around funding appropriations time. So if you're not involved with SPI, please join our mailing list. We love to see you throughout the year. Thank you.
Yeah, thank you for doing that.